So 7.3, just like how we did confidence intervals for population mean, this is a hypothesis test for population mean. So we built up to a confidence interval by doing standard error, margin of error, then finding the interval for a practical case. We are going to do the exact same thing. We wrote the definitions of tests last time, and the time before. We understood what a p-value is. And now we have a specific case where we want to test for population mean. But in order to do the test, you've got to know how to find critical values. We have seen this before. Where did we see this? 6.2, which is confidence intervals. So we've seen this before, but the only difference in this case is things are going to change depending on the test. Last time, or the time before, we looked at 3 different types of tests: right tail, left tail, and two-tail. So if it is a right tail test, the decision line or decision boundary is on the right-hand side. So if the data puts something called a test statistic past this point, then we will reject. So that region is what we call the critical decision or rejection region. So we can't arbitrarily come up with a number and say, okay, anything past that would be high rejection region. We need to have a meaning behind it. And that ties to alpha. We know what alpha is. In the context of hypothesis tests, what is alpha? It's a number, but what is it? How?
Error you accept?
Specifically, some what error?
I'm sorry, no, I don't know.
Type 1 error. Standard error. Type 1 error. It is the maximum probability of type 1 error that I'm willing to tolerate in my test. And the 3 common values are 0.1, 0.05, and 0.01. So the critical value here is determined based on the error that we have. And perhaps I'll do it here. So what type of test are we doing? Left, right, two-tail. Rejection region is on the right side. Right hand. We call it a tail because that looks like a tail. And it's on the right side, hence right tail test. So the amount of error is alpha. So the shaded area will be alpha. So we want to find that critical value, which is a percentile or a t-score. We've done this before with confidence intervals. I believe your book calls it T sub C. Or in a formal way, it's T sub 1 minus alpha, colon, n minus 1. And what is n minus 1?
Degrees of freedom.
It is the degrees of freedom. So once we know or set the maximum probability of error, type 1 error, then I can simply use what to find that value. How did we find that value? From 6.2. Did we do the homework? So from 6.2, confidence intervals, and we wanted to find the critical value. What did we use to find the critical value? The answer is easy. Starts with the letter C. Ends with what?
Oh, wait.
Starts with the letter C.
Yeah.
Ends with R.
Oh.
Calculated.
A calculator. Specifically, what function in the calculator did we use? Inverse T. So in this case, simply inverse T 1 minus alpha n minus 1. And that is going to give us the right or the positive critical value. So if the test statistic, which we will talk about, falls right here or anywhere past that point, we reject the null. Otherwise, we do not reject null. Good. So notice that 0. So we can easily find the right critical value for a right tail test using this. So the case here would be right tail test. And I wrote it as 1 minus alpha because the calculator, the older ones at least, would require the area below. So if the area above is alpha, the area below is 1 minus alpha. Good. What would change if the test is left-handed?
Alpha would be negative.
Alpha would be
So
negative.
no,
Alpha is the probability.
The T of C, T sub C is negative.
The critical value will be negative, and what else?
Would it be a type 2 error?
No.
But it just, instead of 1 minus alpha, it'll just be alpha.
That is true. So based on what Nick said, it has to be negative. 0 is right there. So would that critical value be here or there? On this side. So that would imply the decision region or rejection region, would it be on the right hand side or left hand side? Left hand side. So so the area in this case is still alpha. Previously, that number right there was the positive critical value on the real number line. In this case, that number right there is the negative critical value or left critical value. I believe you called it negative TC. Or formally, it's simply T sub alpha, comma, n minus 1. The alpha stands for the maximum probability of type 1 error under our assumptions that we're willing to tolerate. And alpha is the area below that point, which in this case is 0.05. Or 0.1 or 0.01. And I can find the left critical value by or using inverse T, alpha, the area below, comma, n minus 1. Good. So we took out of a right tail test, and here is a left tail test scenario. That leaves us with 1. What is the last one? Two-tailed test, okay. Now, where should the rejection region be? What does that mean?
Anywhere not in between the critical values.
So one on this side, one on that side. So this would be negative, of course, and that is positive. So we have rejection regions on both sides. And that number right there would be the negative critical value, and that would be the positive critical value. If you go back and look at the last two cases, if I set alpha to be some value, the area corresponding to the critical value was exactly alpha. Here, there, alpha. That's it. What should that area be? It is the maximum, alpha is the maximum probability of type 1 error. And we set it at 0.05. And in every case, the area has to be alpha. So alpha here, alpha there. What should it be over there?
2 alpha.
2 alpha.
Oh,
Divided by 2.
Alpha over 2 or alpha divided by 2. So it's not 2 alpha. So the reason being the maximum alpha, the maximum probability of type 1 error is alpha. So if I set alpha to be 0.05, it has to be 0.05 at all times. So the area here is alpha over 2. That area there is alpha over 2. Would that be positive or negative? Negative.
positive.
Positive. You can use the calculator to find this. T sub alpha over 2. Comma n minus 1. On the other side, T sub 1 minus alpha over 2, comma n minus 1. Inverse T. On this side, same on the other side. And that is for a 2-tailed test. If you do not have a TI 83, 84 calculator, which would give us inverse T, what should we do? We use the table from the textbook. Good. Table 5 in the appendix, t-distribution. Are we clear? So first, we've got to determine what type of test we intend to perform. Second, we need a value of alpha. Third, we find the critical values based on the test we identify. Good. So we want to find the critical value. I'm telling you the type of test that we intend to do is a left tail test. Alpha is 0.25, N is 16. So the first question is, should we find a positive critical value or negative critical value? Negative. Because the rejection region in this case is on the left. We can use inverse T. Alpha is 0.05, so 0.05, comma, 16. Should we put 16 there? No. 16 minus 1, 15. And what do we get?
-1.753.
Good. So when we do the test, when we find the test statistic, if it fell below -1.753, then we would reject. Otherwise, we do not reject. Okay, so two-tailed test versus the rejection region mean. Both sides. So one would be positive, the other negative.
2.453.
Is it necessary to find both? No. You find one multiplied by -1, you get the other. So inverse T alpha over 2. So in this case, 0.01 divided by 2, 0.005, 32 minus 1, 31. And
Oh, wait, my number was wrong.
2.714.
2 points negative, right? So in this case, if the data puts the test statistic below this value on the left hand side or above that value on the right hand side, we reject the norm. Does that make sense? We call it the rejection region because that's what helps us make the decision of rejecting the norm.